Welcome students to lesson 6 on exponential functions. Today you'll be able to evaluate and graph exponential functions by the end of this lesson. Now my worksheet is a little bit messed up here. The concept of exponential functions, we'll be given a parent function and it looks like this: y equals a times b raised to the x power, and a is not allowed to be equal to 0 and b is greater than 0. Now you'll see me refer to this number here. That is the base of our exponent, and here we know that we are dealing with an exponential function because we actually have x as an exponent. So in all of our linear equations, x and y have just been numbers with a coefficient sometimes in the equation. But once x is actually an exponent, it's its own new type of function. And then you'll hear me sometimes talk about a as the start value. So this is the parent form of our equation. And then down here where it says examples of exponential functions, actually these are my two examples. You can see in the top line here, this graph is labeled with y equals 2 to the x power. So if we're looking for an a value, there's not one. So we can assume that a is 1 and then 2 is our base. And you can see that x is my exponent. And so when I graph this, it makes this sort of shape here. If I were to just pick out some points on that graph, if I were to pick x as 0, and I'm going to plug in 2 to the 0 power and get y, well, 2 to the 0 power is 1. And you can see on my graph, here's the point 0, 1. And then if I plug in a 1 for x, 2 to the 1 power is equal to 2. So here's the point 1, 2 on my graph. And I'll do one more. If x is 2, and I plug in 2 to the 2, I get 4. So here's 2, 4 on my graph. And it works also for the negative numbers. If I were to plug in a negative 1, 2 to the negative 1 power equals, of course with that zero product property, equals a half. And so here's the point negative 1, a half on my graph. So you can see it gets exponentially bigger. And then underneath is the function y equals negative 2 to the x. And that is simply going to have, still going to have that sharp increase, but this time I'm going to do a negative, or take the opposite of everything after I plug in x. So just making a little table of values for this function here. If I pick x as 0 and I say, I'm going in the order of operations, so I'm going to do exponents first. 2 to the 0 is 1, and then I do my negative sign. So there's 0, negative 1. 2 to the 1 is 2. The opposite of that is negative 2. 2 to the 2 is 4, and then the opposite of that is negative 4. So all of those points are located on our graph. And then, so this is called an exponential growth function, which we'll get into that in the next unit. And here's what happens if our b value, or our base, is a fraction. So you can see this is y equals 1/2 to the x, and that's going to go downward. And then if I take and put that negative outside of the parentheses, this is the graph that forms for that. So one thing you might be asking is, how can I tell if a function is going to be an exponential or not? So if I'm looking at a table, how can I tell if my function is going to be exponential? So whenever we analyze tables, we kind of try to look at the x values and the y values and what happens with each step up the chart. And so what I notice here, -1 and -3, they have a certain relationship where I can multiply by 3 each time. -3 times 3 is -9. -9 times 3 is -27. So when they have this same factor every time, that means you're dealing with an exponential function. So let me answer this and explain. Yes, they are exponential because the y values change by the same factor. Every time. We call that a common factor. So let's take a look at some of these functions down below. And we want to see what each, so as we notice, our x's are going up by 1. And you should pause the video at this point if you don't want the answers to be revealed to you. So, in letter A, this was definitely a calculator problem. In order to find out what do we multiply by 2 to get 2.6, we have to actually take 2.6 divided by 2. And when we do that, we get 1.3. And so then I want to check each time. If I take 2.6 times 1.3, do I get 3.38? Yes. Times 1.3 every time. So the answer would be yes, they are exponential, and that's because this one you multiply by 1.3 every time. Now here, to go from 500 to 550, we simply multiply by 1.1. And to go from 550 to 6.05, well, I really just have to test this number. It does have to be the same every time. So this one, they all have a factor of 1.1. So yes. And this one, because it's multiplied by 3, or 1.3. This one, it's yes, because they're multiplied by 1.1. And there's 2 more. So hopefully when you did your try it problem, you paused the video and you did these last 2. And hopefully if you did, you found out that neither one of them is multiplied by a same common factor each time. So now let's take a look at example 2. Does the rule represent an exponential function? And I'm looking at the first one and I see an a value or a start value. And I'm looking for up in my exponent, I'm looking for that to be a variable. So since my x is not an exponent, I'm going to say no. But now here I've got an a value, a b value, and my x is in the exponent. So this one would be a yes. And my explanation is that my exponent is a variable. So I did write out the explanation. So let's see how to graph an exponential function. Here I've got y equals 3 times 2 to the x. So I think the best way for you to graph these is with a table of values so that you can see how each point has an effect on the shape of the graph. So I'm going to use my standard 5 points that I always use to graph functions. So if I plug in a -2, I Actually, all right, I'll start with -2. So I'm going to do the order of operations, so I'm doing exponents first. So 2 to the -2 is a fourth times 3 is 3/4. Then 2 to the -1 is a half times 3 is -3/2. Or sorry, is +3/2. So 2 to the -1 is a half times 3 is 3/2. 2 to the 0 is 1 times 3 is 3. 2 to the 1 is 2 times 3 is 6. 2 to the 2 is 4 times 3 is 12. Alright, so I won't have a place to graph all of this on here. But at -2, I'm at 3/4. At -1, I'm at 3/2. At 0, I'm at 3. At 1, I'm at 6. That's all I have room for. But what you're going to see is all these exponentials, they make a little tail going off in one direction and then going off towards infinity in the other direction. So now let's see what happens when I try to graph a fraction. So I've got 0.5 times 3 to the x. So not that that fraction plays a huge role, but let's go ahead and plug in a 0. 3 to the 0 is 1 times a half is a half. 3 to the 1 is 3/2. And let's see about a -1. So 3 to the -1 is 1/3 times half of that is like actually 1/6. So I think I've got enough to go on here. So at -1 and 1/6, there's a half, and then let's see. I think I made a mistake here with the 3/2. I think I meant to plug in a 1 there, and the answer is 3/2. So at 1, then my answer is 3/2. So you can see my graph is still sort of following that same sort of upward trend. Alright, and we actually have one more exponential to graph here. And I'm actually going to show you. So I'm plugging in a -0.5 times 3 to whatever x is. And I'm getting y. So when I plug in a -2, I'm doing -1/2 times 3 to the -2 power. And that's actually a calculator problem, and you're going to get -0.06. So I'm going to do my same 5 x's. I'm going to plug in for each of those. So I get 0.17 when I plug in a -1. When I plug in a 0, 3 to the 0 is just 1 times -1/2, so that's -1/2. Plug in a 1. And I get -1.5. Plug in a 2. And I get -4.5. So let me plot those points. -2 and 0.06. And then 0 and 1. Oh, these are all negative. My bad. So I need to go back and I need to go on the other side of the x-axis. -2, -1, 0, +1, -1.5, +2, -4.5. There we go. So there's certain different things that happen when you have a negative sign here. when you have a fraction here, all sorts of different things, which we'll be talking about in later units. So for now, this concludes a general introduction of exponential functions. Thanks for watching.